All right, well, I say it's 3:30, so let's go ahead and get started. I'm Sarah Woods. Good afternoon and welcome to today's EOL Hybrid Seminar. It's my pleasure to introduce Dr. Partick Veres today. Patrick is a research chemist at the NOAA Chemical Sciences Laboratory here in Boulder. Before joining NOAA as a research chemist in 2018, he received his PhD in chemistry from University of Colorado. He then held a postdoc at Max Planck Institute for Chemistry before returning to Boulder and starting up with NOAA. Patrick's research focuses on the development and application of chemical ionization mass spectrometry for airborne sampling of trace gases. His research focuses on reactive inorganic species, with recent interests that include marine sulfur oxidation, heterogeneous reactions of atmospheric gases and aerosol, and reactive halogen species in the upper troposphere and lower stratosphere. Please join me in welcoming Dr. Veres for his seminar, Observing the Atmosphere Through the Ions of Mass Spectrometry, Laboratory Investigations to Next Generation In-Situ Stratospheric Deployments. For those of you joining us online, please feel free to enter your questions in Slido at the bottom of the screen, and we'll answer them in the Q&A.
Thank you very much for the introduction. I appreciate it. And thank you all for coming in person. And I have no concept of how many people are online, but I appreciate you all tuning in. My name is Dr. Partick Veres. I work currently at the Chemical Sciences Laboratory over at the NOAA. And so what I'm going to talk about today is a lot of the work that I've been doing in the past sort of 5 to 10 years and the road that it's taken to get from a few commercial instruments to really robust field deployable mass spectrometers. This talk's a little unique in that I wanted to give a sort of a higher level view of what we do, but there is a lot of technical details in it. And so hopefully I'll lay that out nicely, but please feel free to ask questions about anything at the end of this. So I don't have much introduction to why I do what I do, or why many of us do what we do, but I do have this slide in here that just kind of points out that to understand the Earth's atmosphere and many of the science questions related to it, we need a really holistic understanding of the atmosphere, both from a dynamic standpoint as well as a chemical standpoint. In order to tackle challenges related to the Earth's atmosphere, we really need to try to stay ahead of that curve and anticipate and identify problems and really lay out a plan to the future, because any instrument development or any project takes a spin-up time that's not insignificant. That's particularly true when we're talking about field deployments on things like large research aircraft, which take proposal stages. It takes planning to get instruments on them, and it takes time to assemble a team and deploy. And when you look at the Earth as sort of a single system, you see that it's comprised of many, many different emission sources, many different processes that might remove chemicals from the system, that are inputs from outside of the system. All of these things interact in a way that we're interested in understanding. As we start to deploy instruments in that space, we realize that the conditions within the atmosphere of the Earth, from surface to stratosphere, vary quite incredibly. Here I'm showing a couple of graphs of altitude, water, temperature, and pressure. And as we put instruments into the field, into those conditions, and scan throughout that space, we often are confronted with a lot of problems and challenges that we face. And so much of the talk will focus on some of those challenges, how we've overcome those, and how preparing instruments for those conditions really puts us in the best place to do the best science. So this statement here is really just it's the soundbite of what I do. I take state-of-the-art instrumentation, and I use that to conduct both laboratory and field investigations to try to push forward our understanding of the complex Earth-atmosphere system. So I've already keyed in on a few of these details, but a main point here, and throughout the day we've talked about it, is that field instrumentation almost never means turnkey. You can't often take an instrument, put it on a platform, whether it's a ship, a van, or an aircraft, and drive it around experiencing pressure changes, vibrations, water changes, temperature changes through the scope of the atmosphere, and expect it to return high quality data. And so a lot of our job is putting together either individuals or putting together a team that have multidisciplinary skills. And so there's a lot of technique development that goes to putting an instrument in the field and monitoring calibrations. There's the environmental dependencies, as I've talked about. We need to understand those and how those impact data in negative ways. and there's measurement interferences that have to do with different sample matrix effects, one of which I'll talk about is high ozone in the stratosphere and how that might affect certain measurements. Engineering and software development is a must. These are things that are challenges to overcome when you take an instrument from either commercial or lab state and deploy it into the field. And so we need a really multidisciplinary team to get and to achieve these goals. So what I'm going to talk about specifically is my journey of doing this work. We start with a commercial instrument that looks like this as it comes from the factory. These are time-of-flight chemical ionization mass spectrometers from a company named Tropospheric Aerodyne. Two companies, one makes the mass spec and one makes the instrument. And what I've done is convert those into two different instruments, one that operates predominantly in the troposphere, which is shown here on the left, and one on the right, which is operated for the stratosphere. I'm only going to touch upon the stratospheric one at the end here. Most of the talk will be about developments over the sort of evolution of this instrument progress from commercial to this tropospheric SIMS instrument. The key message here is that we really need well-designed and developed instruments and also techniques in order to improve our capabilities for atmospheric monitoring and push the science to the next step. Without good measurements that we can believe in, without good measurements that we have faith in their accuracy, we really can't understand the scientific impacts of the data we're collecting. You also need many instruments to do this, and so I'll show you one path, one instrument, but to get a holistic view of the atmosphere, you need dozens, perhaps, of these projects going on simultaneously. So the time-of-flight chemical ionization mass spectrometer, this is sort of a high level. I won't get too technical, so nobody gets too bored with the details, but this is a mass spectrometer. Mass spectrometers are essentially an instrument that is detecting a charged species. So in order for us to manipulate a gas in the atmosphere, one of the easiest ways to do that is to charge that gas. We do that in this instrument up front, which I'll talk about next, but once it's charged, we can guide it down through some optics into a time-of-flight mass spectrometer, which is shown here as a large box. This is a low vacuum region. The extractor pushes the ions down this flight path, and we separate these things by mass. So chemical ionization part of this is the unique feature or the brains of the operation. And so this is where we use the controlled chemical reaction to charge a species. And in this case, I'm showing you a very simple reaction here where our sample or a gas is coming into the instrument. We use iodide I- to cluster with that sample gas. And then that cluster, which is iodide plus the gas, would then be charged and directed down into the time of flight. I'll spend most of the talk talking about iodide SIMS, this I- SIMS sequence. It's not as simple as I put it here. I'll get into some of those details. There are many different versions of this, as I'll talk about on the next slide. Once we get to this extractor and give things a push, what happens is that things are separated by mass, where the lightest gases go the fastest and the heaviest masses are much slower, and we get data that looks something like this in this inset. Where on the left side of this x-axis, you have really light molecules arriving at the detector first, and as we go to the right, we get heavier molecules coming out. Each of these vertical lines is a different gas that we're detecting in the atmosphere. And so this spectrum here is showing something like, let's say, 1,000 different peaks. Some of them come from the instrument, some of them come from the atmosphere, and some of them are secondary dirty chemistry. And so sorting out the details of what's in this data set is most of the job of running one of these instruments. So SIMS techniques can detect a wide range of molecules. I just showed you that one detecting, or seeing thousands of molecules there. We talk about organic compounds in a volatility space where high volatility things are like acetone, methanol, alcohols that you can smell. Low volatility things are very sort of waxy type compounds that maybe aren't in the gas phase but prefer to be in the particle phase. And so I'm just going to put some of these techniques on this axis just to give you an idea of where and how we can measure these things. So H3O plus is the most common of these ions, PTRMS. It measures very volatile compounds, lightweight organic gases. That's been in use since around 1995. 98 or so, we get the ammonia ion, and this has been generationally improved to operate differently, but we look at organic acid, ketones, multifunctional organics, and that pushes things into another chemical space where things are a little less volatile, so more likely to be in particle phase. Acetate ion is an ion that I developed in my graduate work. Acetate ion fills a gap that starts to bring in inorganic acids like HCl into the equation, so we can detect strong acids. CF3O minus is been used for a long time, but it's very selectively used by a few research groups around the country and globe. The big powerful part of that are hydroperoxides. It's similar to acetate in its space. I'll talk a lot about the iodide SIMS in the coming slides. That fits a space that pushes a little more into low volatile, so more likely to be in particle. And the lowest volatility is nitrate. Folks have used that for a very long time, since 1991. Lee Malden, who is in NCAR, has used that in his past. This detects very low volatility things that almost certainly are going to want to be in particles and things like sulfuric acid. So SIMS instruments, many of you who have been on aircraft projects have probably seen these across your table before. They're becoming more and more prevalent because of the number of observations you can provide with a single instrument, and also the breadth of detection that you can achieve with these things. And so on the Aroma project, which is a project that I'm co-PIing that'll take place in 2023, we actually have 5 of these things deployed on one aircraft. This is becoming more commonplace with both ground site and aircraft, and so I showed you this volatility space on the previous slide. This suite of instruments basically spans the entire range of organic compounds that we might want to detect. On top of that, we're getting a lot of inorganics and other compounds of interest, which I'll go into. But again, I'm going to focus pretty much solely on this iodide SIMS because that's my expertise and the instruments that I'm used to working with. So this figure I've shown you already once. This is the iodide SIMS now, and I've simply put that generic equation up at the top again. We have a sample come in, we react it with I- ions, and we do all of the stuff that I just spoke about. We generate I- ions historically with polonium radioactive sources. So this is a process where the 210 polonium emits alpha particles. Those alpha particles collide with methyl iodide, and they produce an I- in the process. And so this is historically how we've done this. There are problems with that. Radioactive sources are never fun to deal with. They have a lot of regulations on their use. In the recent years, my group has worked with Greg Huey out of Georgia Tech to develop this krypton vacuum ultraviolet lamp, where we can take methyl iodide through this commercial lamp and photolyze it into I-. It has a huge range of benefits. It's a big step forward in how we're able to produce ions in these instruments. It means no more radioactive sources. Almost certainly within the next 5-10 years, nobody will be using radioactive sources for this use anymore. There are big reasons to appreciate it in foreign countries, especially where use of these types of sources is completely prohibited. So in Asia, there are a lot of regions where you can't even deploy these on ground sites. And so building this technology has kind of opened up the science to a large range of people. They're commercially available, they're cleaner than the previous sources, and they have improved stability. And so this is how we generate ions currently. And it took a lot of iteration to get there. So iodide SIMS is historically used in its first incarnations to measure PAN. PAN is peroxyacetyl nitrate. It's an important organic that transports NOx to remote regions. So here's the scheme of how we detect this. We would take it into the instrument as PAN, heat it up, decompose it into this peroxy radical, CH3CO3-. It then reacts with an iodide or an iodide water cluster and removes an oxygen and gives you this acetate ion. That is how you would detect PAN on the instrument, as acetate. It also happens to be how we ended up developing the acetate SIMS, was dirty chemistry in this scheme. We still use this today to detect PANs with this instrument, but since then we've realized that the iodide SIMS has a lot of application with other trace gases in the atmosphere. I'm showing a scheme here that detects nitric acid, but it's a generic reaction where you take iodide, it clusters with water, so you have some mixture of iodide and iodide water in your reaction region. That can then cluster with something of interest like nitric and give you the I-nitric minus ion, which you then can detect. And so there are 2 detection channels in this instrument. I'm showing it for nitric and PAN. It's very widely applicable to many, many species. And so for a long time, iodide has been used for its flexibility and the simplicity of generating the ions and detecting and understanding what you're seeing, because everything should be detected as a cluster with iodide. So you're not fragmenting molecules. It's very simplistic in what you detect, or at least that's what we thought it was. This has been used for N2O5, HONO, halogen species, and miscellaneous species PANS, as I mentioned, HPMTF is a sulfur molecule I'll get to in a little bit, hydroperoxy methylthioformate, and organic nitrates. The catch, though, is that after a long time of operating these things, a decade or two, we've started to realize in the past 5 years or so that nothing is as simple as it seems, and there's a lot that goes into understanding what we're seeing with the instrument and trying to get that correct. And that's even more important when you're doing aircraft observations and parameters are changing so rapidly. And so I'm going to go through a number of challenges that we've encountered with the instrumentation and how we've overcome those challenges and put that together to do a little bit of science. So challenge one is that the iodide SIMS mass spectrometer doesn't give you an ID. It doesn't tell you exactly what the molecule is. What it gives you is a very exact mass, and it gives you a mass to 4 decimal places with an error of about 0.01 mass units. And so this figure here is kind of showing you how good this is at separating masses at a single mass unit. So every one of these molecules, as we would talk about them in normal science culture, has a mass of 201. This instrument breaks that down to even smaller, finer levels where we can now look at 3 molecules at 3 different masses at nominal mass 201. And so if we look at just a single peak here, this yellow peak is In-Situ The mass that we're detecting of 200.9043 is so exact that there are only a select number of combinations of the elements in a periodic table that can give you that exact mass within the error of the instrument. And so because of that, we can run a simulator that basically tells us that, okay, this has to be this molecular combination, IC2H2O3 minus. And so we're able to really unambiguously identify a molecular formula from that. The I minus comes from the chemistry, so the rest is just the organic. And so this molecule that's showing up in yellow is C2H2O3. And that's great, except we don't know what molecule that is exactly. It can have multiple isomers. I'm showing you a simple case of a molecule with only 2 carbons, and there are 2 options for what that can be. I can rule these out based on science and sensitivities of this instrument. I can make standards, I can put them in and see if the instrument sees both. When we get to compounds that have C8, C9, C10 numbers, you get to isomers or different molecules at the same molecular formula in the numbers of 5 to 10, and it's almost impossible to understand the difference between those. This is just a fundamental problem with the technique. This is a technological problem. We detect the mass exactly, we get a formula, but we can't tell you what the molecule is without additional work. And so that is one problem. The other problem is sometimes you don't separate masses very well. In this case, this ICl2 peak, this is chlorine. It's an isotope of chlorine. We can separate these, the yellow and the blue, quite well. We can curve fit that and get data. But in all cases, that's not true. Sometimes these are 2 on top of each other to resolve. I say this is a limitation, but the technology is changing. And so the figure I'm showing you initially is from sort of a 2010 era time of flight. As you make the time of flight longer, you increase the separation between peaks. And so this blue curve here is approximately what I'm showing you in this figure that I've put together. In this commercial figure, you see a future iteration that came about in 2018 that's just a longer version, has really solid separation between many peaks that show up as 2 peaks in the previous version. So technologically, we're moving forward. It's just the limitation here is technology and not the technique itself. So calibration is a big deal for a lot of instruments. Pretty much any instrument I've come across needs to be calibrated. There's a problem with this technique, just like every other problem, except absolute optical measurements. This is not an absolute intrinsic calibration. We get a molecular formula, we get a signal. We cannot tell you how much that is in the atmosphere without a calibration. And so we spend a lot of time developing calibration methods. Those sensitivities differ by molecule. So you can't apply one sensitivity to every molecule you look at, and each molecule has a different dependence on pressure, humidity, and temperature. And so the number of variables as you start to multiply them get so out of control that it becomes really impossible to calibrate for every species at every condition. But we try. We do a lot of development of cal techniques. I don't need you to understand everything that's there. It's 4 examples of, collectively probably 6 months to a year of work each of developing individual cals for a species. The left is pan. Then as we move to the right, we developed a source for HONO or nitrous acid. HPMTF, which I'll again talk about a little later, and organic nitrates. We are currently working in my lab to develop calibration methods for those. And so we put a lot of work into those, but again, each one of these molecules has a pressure dependence, humidity dependence, temperature dependence. It's just an impossible problem. And so calibration at all conditions for all species is really not feasible. So we handle this by improving the stability of the instrument. We basically want the instrument to not understand that it's flying through space and time with varying conditions of pressure and humidity and temperature. And so that's what the next few slides are. So our third challenge I'll talk about is related to that. This is pressure dependence. So this chemistry is pressure dependent. As we fly around in an aircraft, as one might, the pressure is going to change dramatically from the surface to high altitude with a reduction of pressure as you go up. If you just let the instrument experience that pressure change, what happens for something like chlorine, which is forced by a reaction of iodide water and chlorine, is that this reaction, the collision frequency increases, which means we form more product ion and our sensitivity goes up. So this figure here is a signal or a sensitivity versus the pressure of the instrument. The IMR is the reaction region we're doing the chemistry in. And as we increase the pressure of the instrument, we increase the sensitivity. So in flight, if we didn't control pressure, we'd need to account for this. And again, for every molecule we're interested in, which could be dozens, we'd need to know this curve and correct for it every time. So we developed a pressure control system on the front end of our instrument, showing sort of from the bare bones schematic I showed before, this IMR region where we have I- that's doing the chemistry. I kind of stopped there before. On the front end of that, we've built it out to build in pressure control strategies as well as a few other things. So the figure here that I'm showing in this aqua color is ambient pressure. As we go from high altitude on the left, we do a descent into the continental boundary layer and the pressure goes up, and then we do a climb back out of that and the pressure goes down. And so across this pressure range, the instrument would experience great sensitivity changes. So what we do is we actually actively pump between two critical orifices here, and we do a variable pumping between those orifices. That effectively isolates where the chemistry is happening in the IMR from the atmosphere, and the instrument doesn't see the changes due to pressure. So on this graph here on the left, in sensitivity space, we'd really just be sitting at one of these points, no matter what the atmosphere is doing outside of the plane. To show you how effective that is, we have on the left here IMR or inlet pressure in gold, and that's the pressure of this region highlighted in gold, quite constant across these altitude ranges. We also actively control the IMR pressure as a redundant pressure control, and that is also flat throughout a flight. So this system effectively removes the pressure dependence of the instrument as it relates to sensitivity changes and allows us to more rapidly and more accurately determine concentrations from signal. In a simple world, this means that we should operate the instrument at the highest pressure because as the pressure increases, the sensitivity increases. But we're doing aircraft work and nothing simple, and so now we have to worry about dirty chemistry in the instrument. These are all things that are observations that have been field-driven. So as we deploy this instrument, we encounter a problem, and then we fix that problem. And because we fix that problem, we can now see a new problem, and now we have to fix that problem. And so each of these challenges are peeling back the layers of this technique. This is sort of common, I think, amongst many instrumentation that you might deploy in the field. And this one, we started to realize as the stability of the instrument was improved, that we could see these signals related to ambient ozone. And so what happens in the iodide system is that we detect ozone fairly well, and that shows up as an ion IO minus. And IO minus happens to be a very, very good clustering reagent, much like iodide. And so iodide can react with something like nitric to give you an iodide-nitric cluster. IO can also react with nitric, and it gives you something that looks like IO-HNO3. And HNO4, which is what I would interpret that as, is peroxynitric acid, which is a molecule that we actually have atmospheric interest in. And so when we see this in the instrument, and my gut interpretation is, oh, we've just measured peroxynitric acid, I would be completely incorrect in assuming that. And so this is chemistry that we only recently started looking at that has been occurring in the system and being misinterpreted for years that we're trying to understand the dependencies of. And so this is a pressure-dependent process also. And so here on the left figure, I'm showing this IO minus, which is the dirty clustering reagent ion, and as we increase the instrument pressure, the concentration increases. The dirty chemistry, the peroxynitric acid is also increasing with pressure. And so this is telling us that, boy, we can't just put the pressure as high as we want to increase the instrument sensitivity. We have to be aware of secondary chemistry. And so there's no solution to this that we found yet. The only solution is using the lowest pressure possible. But the problem is now we've reduced the pressure, we've reduced the sensitivity. And so we have a balancing game of what are we trying to measure, where are we trying to measure it, and is this impactful on those measurements? And so being aware of the problem is really the best solution at this point. We have a humidity dependence. Most instruments have this. There's hysteresis effects, but there's also direct humidity dependence. So I've kind of given simple reactions here, but this iodide water making iodide water cluster is a reversible reaction. The more water we put in the system, the more we force the reaction to the iodide water cluster. The problem with that is that molecules have different sensitivities to I- versus iodide water. And so as you shift that equilibrium back and forth, you change the sensitivity of molecules differently from each other. You can also reverse the reaction of the product formation. So we see everything as this iodide clustering with a gas. That's also reversible. So as you increase the energy, that might go backwards, and I'll talk about that in the next slide. But typically, historically, we knew that water was part of this chemistry. Adding water boosts sensitivity of the instrument, so we've done that. We do that with a fixed flow historically, and we just always chose 10 cc's because it was okay, it worked. We flew around the world during ATOM, and I can monitor the ratio of this iodide water to iodide cluster directly with the instrument at 1 hertz. And you get something that looks like this after you fly around the globe on a project like ATOM. It's not very stable. Every time that moves, the sensitivity for each molecule changes, and we have a non-ideal situation where we have to correct for those dependencies. So between ATOM 3 and 4, I developed a method to do dynamic water addition. So we're monitoring in real time iodide water and iodide. We ingest those measurements, we throttle the flow through a bubbler, and we counteract the effects of ambient water being sampled into the instrument. And now we have stable measurements of sensitivity as it relates to water. The step changes there are actually somebody on the plane pushing that number around. So you can see it's quite constant when we're not doing anything, and then you switch and give your colleague the instrument, and they start changing these ratios, and it changes sensitivities. But that's mostly due to a need to do that from atmospheric water. But in order to understand your measurements, this is really a necessary component of this. It gives the instrument the stability so that the sensitivity isn't changing dynamically as you tour the globe and make measurements. So the last one I'll mention is that iodide Sims chemistry is very temperature dependent. We really only recently identified this during a field project. It should have been something that was blatantly obvious to us. If these reactions are reversible and these clusters are held together by some binding energy of iodide to a neutral, if you heat that up, it should reverse that reaction. And it wasn't something, we were so focused on all these other problems with the instrument, we weren't looking at the effects of temperature. And if you've been on an aircraft, you know that the cabin temperature swings quite dramatically as you go from high altitude to low altitude, or you go from the beginning of the flight to the end of the flight. And so we started to notice this, we started to probe this in our system. We did some experiments that are shown here in the top right. This is a graduate student that's working with me. As you heat up the system, the sensitivity of the instrument drops. So going from right to left is cold to hot on this graph because it's 1 over temperature. And so the cooler the instrument gets, the higher the sensitivity is. So the more we're favoring the formation of this cluster. This is really important. This figure shows this. It's from ground site observations in Pasadena, California this past summer. Sorry, not this summer, 2021 summer. I'm breaking down this graph. The pink curve here, these are diurnal profiles of temperature and formic acid. So the pink reddish curve is the temperature the instrument is experiencing in the cabin. It's actually the instrument temperature. You can see that as the sun rises, the instrument gets quite hot in the little trailer we're working in, and then it cools off as the sun sets. If we look at the way we used to calculate sensitivities and concentrations, formic acid, which is in this greenish color, actually is reduced during the daytime, the way that we would analyze data as of a year ago. Once we realize these temperature dependencies and you correct for them, we get a complete flip of that diurnal trend. And so we see what we should see, which is formic acid is produce photochemically in urban regions. And so this has huge impacts on the interpretation of data. In most cases, it wasn't an issue because in a lab environment, temperature is not changing. Even on aircraft, in most cases, the temperature is fairly stable. This was an extreme case where we had daily fluctuations in temperature ranging from anywhere from 5C to 10C, and so it manifested in the data quite significantly. So, the lesson here is to temperature control the instrument, which again should have been one of those obvious things, but there were so many other problems we were chasing that it kind of fell down the list a little bit. But not only do we need to stabilize that, but we can leverage this and cool down the instrument to make it more sensitive. And so we're currently in the process of doing experiments to understand the effects of cooling the instrument down and how that might bring us advantages in monitoring species in the atmosphere. So to take it all and put it together, that's the goal. We have this aircraft instrument. We want to go out and we want to measure. I just went through all of that because I think a really important part of the story of how we get to the science or the pieces of the instrument we put together to know what we're looking at. I'm going to show you a couple slides of science, in particular from ATOM and this HPMTF molecule we discovered. But getting there and trying to interpret that science really required us to have a lot of faith in the instrument technique and the data we're looking at. And so putting all these pieces together, both for previous projects and for future iterations and deployments, will really help us to have trust in the data and lead us down a path that'll make, hopefully, these instruments more hands-off and less that we have to babysit them while they're on plane. So most of the work I just talked about was iterations that came from ATOM and FireX. Like I said, Aroma, many times today, we're planning this Aroma project that'll be the next flight of this instrument. But I want to just briefly talk about ATOM, NASA ATOM observations. So many of you are aware of what ATOM is. ATOM was a series of global flights going from pole to pole. The sort of global map here on the left is showing the 4 flight tracks of ATOM going around the globe. It was constant profiling, so it was something like 10 minutes at the highest altitude, and then we'd slowly descend to about 500 feet, and then fly at about 5 to 10 minutes at the lowest altitude, and then just return to the upper atmosphere. And we did this across the entire globe. So this was a really remarkable project, a huge data set. A lot of people in the room were involved in that. The NOAA SIMS, the NOAA iodide SIMS, was only involved in the 3rd and 4th deployments of this project, so it was a late addition to the payload. We had to sort of we built the instrument for the project, and then we had to propose to get it on the plane. So we kind of put the cart before the horse on this one a little bit, but we ended up getting on the plane, and it was extraordinarily valuable. So when we flew this around the world, we noticed something. I noticed something in the mass spectra that really perked me up a little bit. So one of the primary goals of ATOM was to look at this molecule N2O5, which I'm showing here as the cluster of iodide in N2O5. That molecule is important for storing NOx during the nighttime. It reacts on particles to liberate ClNO2, chlorine nitrate, which gives you chlorine radicals and kicks off some chemistry. And that was one of the chief goals of this. We started looking as we went from the upper troposphere. This is a raw data, but it's in black. I don't need you to really truly understand what's happening here, just that there are differences. So as we were in the upper troposphere, we see for our iodide water, we see this nice peak on top of the same peak that we see once we get down low over the ocean. And then if we look at another peak that's in the spectra all the time, I3-, which also comes from producing ion chemistry, we see, again, these two are right on top of each other. When we look at the N2O5 peak we were interested in, and the reason I looked at this is as we got over the ocean, we started to see what we dubbed N2O5 by the instrument. Physically, in the middle of the day, N2O5 shouldn't be over the ocean. And so we looked at the spectra a little closer and see that in the high altitude, you see a peak that's N2O5, and at low altitude over the ocean, it shifts ever so slightly. Oftentimes, this would just get ignored. The difference between those exact masses is 0.0074 AMU. The error in the mass units that I told you at the beginning was 0.01, so this is close enough that you could ignore that. But chemically, there are reasons to not ignore that. And so after pushing on it for about a year in the lab after ATOM 3, And going down some roads that were unintended, we arrived at the identification of this molecule as C2H4O3S. That molecule, it took a long time to figure this out because that molecule doesn't exist. No reference had a molecule of C2H4O3S. We had to basically just figure out how it was made, where it came from to understand what molecule it was. As we worked through that process and looked at the global maps here, which were crucial to understanding that, you see a correlation of HPMTF, which is colored on the track and size. So we see hot spots here and here on ATOM 3, where seawater DMS is lighting up. And so we're low over the ocean, it has a sulfur, it likely comes from DMS. That's the starting point for a discussion that leads us down a pathway to unambiguously identify this molecule. Not only did we see it for the first time, we also had this extraordinary ATOM data set that allowed us to do a lot of science with it. I like this slide a lot. Max Boykoff is a CU professor. He tweeted out once this paper came out that we need to basically update teaching content because that's how big of a change this is and a departure from how we understood the atmosphere before we found this molecule. So the system as it existed pre-seeing this was dimethyl sulfide would come out of the ocean. It's made by phytoplankton. It naturally partitions the atmosphere. It reacts with an OH and becomes a proxy radical you see here. You add an oxygen, you see that. And normally, typically, this would either turn into sulfur dioxide or you'd get another pathway that would take you to MSA. And that's the world as we knew it before ATOM. 20, 30 years of science was written on that. Seeing this molecule in the atmosphere truly deviated the chemistry from a world where over 50% of the DMS sulfur would end up as sulfur dioxide to a world where about 30 to 40% of the DMS sulfur ends up as HPMTF, and that's what's shown here. So before we saw this orange bar would have just been gold as we understood the chemistry. It was a molecule that was invisible to us. It was a molecule that had been theorized to potentially exist through some really unique chemistry where this molecule kind of attacks itself and bends over and folds and creates a new molecule doing that. But it had never been seen, it had never been validated, and it had actually been sort of archived as something that was unreasonable to happen in the atmosphere. So this discovery really changed things a bit. A change like that really gets people excited. A lot has happened since 2020 when we published that. So we come out and we say, before this molecule, we had a SO2 and MSA from DMS that looked like this, and now we're going to take a chunk of that SO2 and make it HPMTF. This has been validated. This is how the atmosphere works right now. Later, Vermeule from University of Wisconsin measured oceanic deposition fluxes at the Scripps Pier and then implied a rapid cloud loss for that. It's something we also implied in our paper. 21, a group did chamber studies, and this is certainly not comprehensive, but a group did chamber studies to quantify the formation rate of HPMTF. Now we can put it into models and understand how fast it's being made. Novak et al., Gordon Novak currently works with me, was at University of Wisconsin. We planned a flight during the FireX SARP project for NASA, a 2-hour flight off the coast, and we were able to measure the uptake rate of HPMTF into clouds. If you put that into models, you see it rapidly alters the sulfate system across the globe. And in 22, more research is coming out. Chris Jernigan, who's also from University of Wisconsin, identified HPMTF as a significant source of OCS. That's a very important molecule for transporting sulfur from the surface terrestrial and oceanic to the stratosphere, and is chiefly responsible for making sulfate particles and sulfuric acid in the stratosphere. And so it's changing how we understand the surface or the ocean emissions coupling to the stratosphere. He also measured aerosol uptake rates, and finally there's some new work coming out that's putting all of this together into models with the cloud impacts and trying to understand how it's changing the radiative forcing of the DMS system on the Earth's climate. And so this, over a very short period of time, has rapidly intensified and really unlocked a lot of secrets that prior to finding this molecule, we just couldn't see it and didn't understand it. So this Aroma project that I'm a PI on that's happening in 23 is in part going to focus on this question, sort of this whole system down in the left here of how do you go from DMS to aerosol sulfate? How do you get to OCS? What are the impacts of this chemistry and clouds on that system? So we're looking to get a lot more data on this in the coming years. But one very significant point is that the iodide SIMS currently is still the only method for detection of HPMTF in the atmosphere. This is important because it limits what we can do and what data sets we can collect. If you want to study the system, you need an iodide SIMS now. That would be nice if that wasn't the case. The more methods that can detect something, the more we can believe in them by comparing them, and the more data that we can get by deploying more frequently. And we need to do that. And so I say for now because I guarantee over the years more will come out in that sense. So the last couple slides I'm going to show here are on the deployment. So that was a tropospheric instrument and a lot of the steps that we've taken to understand that. I would argue that without doing that, we wouldn't have the pieces to put in place to build an instrument as ambitious as what I'm about to talk about. So in 2018 or so, Congress approved funding for NOAA to study activities that might lead to reflectivity changes in the stratosphere or in the marine boundary layer. And so these are climate intervention strategies like aerosol seeding in the stratosphere or marine cloud brightening. And so my team identified a science challenge that was, if we're going to start perturbing the stratosphere, we need to understand the chemical consequences of that as it relates to ozone destruction, halogen activation, many of the things that we've been interested in for many years, we've been regulating for many years. If we go and perturb that system, do we heat that back up and start destroying ozone again? And so we proposed very ambitiously to develop an iodide SIMS instrument that would deploy in the stratosphere. The only means to getting to the stratosphere at the time, and probably still with a payload large enough, is the NASA WB-57. It's an unpressurized aircraft, and so there are a lot of challenges with putting an instrument in that environment. We proposed to look at halogen species, BRO, BRCL, ClNO2, Cl2, some reactive nitrogen species, HONO, N2O5, and organics. And the idea is to make a flexible instrument that can really measure the swath of everything that we might be interested in, both today and things that we don't know that we're interested in the future. The figure here kind of summarizes a lot of the core interests of the iodide SIMS in the stratosphere. We're looking at nucleation processes of low volatility organics, as I described on that first slide of why we choose different techniques. Gases will condense and form new particles. Those particles will grow, and those growing particles will do chemistry or reflect sunlight. We get chemistry on polar clouds that activates chlorine. Once you get these two species, they can photolize to make chlorine, which destroys ozone. And so can we take this instrument, which can measure all the species shown on the slide, with the exception of the chlorine radical? Can we take it up there? Can we learn something about the stratosphere that we don't know already, and then be ready to, again, monitor once or if perturbations are occurring in the stratosphere? We need a baseline in order to understand changes. And so there's a big push to do this fast. So we assembled a team that was ultimately 5 people, 6, including myself. Drew Rollins is the co-PI on it. We have engineer at NOAA, Rich McLaughlin, who's helped. Samantha Lee does programming for our instrument. And Martin Breitenlechner and Gordon Novak are both research scientists that work in our group. And we took, once again, a commercial instrument, which is shown in the bottom left here. We go through a lot of design challenges, a lot of engineering, and turn this from a commercial instrument through a CAD drawing into an actual deployable functional instrument, which is shown in the team photo there. So this is a really heavily modified time-of-flight SIMS. I'm not saying iodide because it's extremely flexible in its operation. It can be installed on the WB-57 and exposed to ambient pressure and temperature. This is a problem because high voltage electronics will arc. It's a problem because the instrument cools down to sub-zero temperatures, and when it lands, it's soaking wet, and that will cause a lot of damage if you don't prepare for that. And so crucial steps to this were trying to pot cables so that they wouldn't arc. We had to build enclosures for high voltage power supplies. The water issue required absolute full automation where the instrument was shut down on its own on descent so that nothing was on by the time water was condensing. The ambition in this project comes both from the engineering challenges of operating in those environmental conditions, but the automation had never been done for an instrument like this. Moving from a commercial instrument that requires a person sitting in front of it to turn it on, operate it, and shut it down to a fully automated, remote deployable instrument. Those are the engineering changes that aircraft work gives us that someday will be adapted to additional instruments. We talked a little today about putting in, one of these in a pod, and when we asked how we should do this, they told us put it in a big sealed can and just seal the whole instrument in there. It's not elegant, it's bulky, it's very heavy, and so we put a lot of time into doing this, but everything we learned could be used elsewhere. Part of this was developing a new ion source, so I mentioned the VUV ion source that we developed with Greg Hughes' group. Here I just have an inset picture of the drawing, so we worked to develop a new version that would couple onto the front end of these commercial instruments. It's very flexible, it can be used by anybody to generate ions. It encompasses, as part of it, pressure control systems, water regulation, inlet flow regulation, and so the design of that is really compact, it's very flexible, and with it we can produce most of the ions that I mentioned in the page looking at the selectivity of different ion species. The only one that we haven't been able to produce is H3O+, and we're on the cusp of being able to do that. Once that's done, or once we can prove that that can be done, you have a one-size-fits-all instrument that can be deployed for any type of molecular species, and an instrument that you can put somewhere and have a pilot flip a switch and it'll turn on and shut down when it needs to. And so this is kind of going from the commercial instruments we started with through that tropospheric instrument, through those deployments and the improvements on that. We've moved much further than that to have this instrument that really, I think, outlines the future of aircraft instrumentation, regardless of the complexity, where we have the ability to fully automate, reduce people time, reduce their worry about whether the instrument's going to work or break. But I'm sure there's a number of challenges we haven't even seen. We have an upcoming second deployment in March of 2023. But this is really only possible through these innovation steps that I've shared with you and the right team of people. That's an absolutely crucial step. So the last slide I want to share is just kind of a conclusion there. There's lots of faces there. You can't do this without a team. But scientific discovery, at least in part, I don't want to close models or any of the other methods that we use, is and can be achieved, and real discovery is achieved through ambitious and dedicated instrument development and deployment. Really understanding techniques, having confidence in those techniques is how we are able to make really large steps forward in the science. You need to identify and address the problems and prepare for them and look out to the future for what is it that we should be doing. In this case, it was, let's look at the stratosphere before we start modifying things, because the chemistry before is as important as the chemistry after. Design an approach to data collection, aircraft, ship, whatever it may be. I think this third one's really the key step here, is to assemble the right team. Engineers, programmers, leaders at all skill levels, all degree levels. It doesn't matter. I think you find the right people for the team. Then you need to create the opportunities to test these, because the iteration process of deploying, saying you did it wrong, and fixing that, and saying, wait, we're still doing it wrong, and fixing that is the only way to make a measurement better, and committing to the continual development of those techniques. And so with this sort of holistic approach, and really scrutiny of the measurement, you can really achieve scientific progress and discovery, even when you're not looking for it, in the case of the ATOM measurements. So that's all I've got today. I really want to thank all these people. There's far more people than you can fit on a slide, but these are most of the folks who have done a lot of the work I've talked about, and design, programming, lab work, from graduate students to senior scientists. So thanks for your time, and I'll take any questions.
Thanks, Patrick, for that very interesting seminar. Brett has kindly turned on the ceiling microphones for us, so I won't need to run around with this. Do we have any questions from anyone in the room?
Yeah, I have a question about, so you purchased the SIMS instrument, So then the process of like doing that integration, or it looks like even taking apart to some extent, having to modify it, all of that, like, how does that work with the companies? Are they willing to share that stuff, or do they tend to be a little bit cagey about intellectual property?
Yeah, there were certainly occasions where NDAs were required. So the company that we work with for these instruments, Toffwork builds the mass spectrometers, which are really the heart of the instrument. Aerodyne you can think of as a customer service organization that sells their TOFs. And so Aerodyne's model has always been to work with the people who are developing the instruments to find their commercial product and advance it. It's a model that works both ways. So, we get to work with that company and get details about the instrumentation in order to improve the instrumentation that they might adapt and commercialize. And so maybe someday they commercialize the science source exactly as we've built it, for example. But because of that mutual sort of agreement or support in development, they're willing to share the details that we need to understand where are the weak points when we go to fly this thing. There's no better person to say, where are the power supplies? Are they temperature sensitive? What are the components that you think will break? Which ones don't you think will break? And so we've been very open communicating with them at the beginning before we even had the instrument. What are the first steps we should be taking? And then we just actually met with them about a month ago or 2 weeks ago to give them sort of the wrap up of, here's what we did engineering wise to get your instrument to function, and here's how it functioned. So it's a two-way street with them, but there were NDAs. Any company doesn't want their technology being stolen, particularly if you can, you could buy this and you could reverse engineer it, or we could try to build one. I'd never do it as well as they can, which is why we buy commercial in the first place. The bigger part also is the customer service side gives us the analysis software and supports it and pushes it. And so they're actually a really wonderful company to work with and ask for changes in software, ask for changes in instrumentation, and adapt. So that was a worry going into it. And we couldn't have done it without them being somewhat transparent about instrumentation.
So what happens with the intellectual property of what you developed in that process?
So, NOAA's kind of interesting because we have a lot of series university scientists. And so with the science source, we had considered doing something like that, getting a patent or something on it. University has first crack at it. They can choose to do something with that or not. And if they say no, then NOAA could take that and do it. For something like this, we decided that that it's not widely applicable enough that you would sell enough to make it worth anybody's while to do anything with it commercially. There are a handful of scientists across the globe that would love to have it, and I'm sure that there are people making similar things right now. But most of the technology that we develop, we are going to publish on, we're going to share with the community. There was a discussion about that two-way road, that it really is beneficial to keep that road open because if we give to the community will give back to us. And what you don't want to do is create a bunch of technology and then have somebody else do something better, and now you're locked out of getting that without a big price tag. And so we often find it's more advantageous to just develop and share openly than to go through those. But NOAA does like to capitalize on patents and have those. And so it's always an evaluation of technology. I don't think anything we've done for this project is commercially adaptable because it's so specialized. There are a lot of people that we know that would want to do these things to instruments, but your market's quite small in a sales world. You might sell 30 units at that cost with the engineering, not 3,000 or 30,000. So same reason you wouldn't, this isn't an economy of scale instrument. You can't put these across the globe at monitoring sites because it would be too expensive and costly.
Brent?
I was just curious to hear a bit more about the discovery of HPMTF. Did the N205 peak go away as the plane went down, and then this other peak appeared when you got in the boundary
No,
layer,
unfortunately
or
not.
Did you think it was N205 all the way down?
I mean, I think it was the first flight of ATOM 3. We flew directly south out of California, and this is where part of the fun of aircraft flying comes in, is we happen to be streaming that peak, that data to the flight data center, and Paul Wenberg, who's at Caltech, got on and said, "Hey, there's N205 down here," and I was looked at the data. I was like, "Oh, you're right," and he's like, "Are you sure that's N205?" And I thought about it for a second. I said, "No, I don't think it could be." And so we had an in-flight conversation about how chemically that can't be true. In flight, I can't do anything about that. I can just sit there for the next 8 hours and think about it. But we got off the plane and I looked at the data, and it was subtle, but it was apparent within about an hour of the flight that there was something else there. It's low enough mass. Again, this is, you have a mass, and what are the combinations of elements that can give you that exact mass? The lower that mass is, the easier it is to identify the exact combination. And so there were only a handful of things that could fit. And so I had a molecular formula within like 2 hours of being on the flight. Now, going from that to what it actually was took a year and a half of work to figure that out. And that's actually, I'm going to stand on my soapbox for a second here and say, when you publish molecules, you should always publish the condensed molecular formula, like C2H4O3S, because it was originally published in theory as a functional formula. So it was HOOCH2SCHO, and it was non-searchable in databases. And so had I had that paper had a condensed form, it would have saved me a year and a half of work to Google it and find that paper right away. But it took we actually had to come up with the full chemistry ourselves to get the structure, and then I was able to search that paper. So that's just the chemist thing, I guess. But no, we knew pretty fast it was not an N205, but they do bleed. So as you go up in the atmosphere and it cools, N205s thermally decomposes. So as you go up in the atmosphere cools, you get more N205. And so you have this sort of curve that N205 is increasing, and as you come down, HPMTF is increasing, so you kind of get this C-shaped curve where there's no 0 point because they overlap. And so I actually, in the data analysis, just cut from this altitude to this altitude. We can't look at that data. There's more sophisticated ways of doing that now. And on aroma, for example, I'll run with a hot inlet on the front, and that'll decompose the N205 before it gets to the instrument. And that way, it won't be an interference on the measurements. It has the added benefit of giving us the pan chemistry, which I talked about earlier too. So we're taking away N205 measurement capabilities to give us HPMTF cleanly, but we're also adding pan observations to the payload. So it's a trade-off, as most things are.
Okay, I don't see any questions online yet. Any others from in the room? Yep, Eric.
Just to follow up on that, how do you get pan if you're heating up your inlet?
Yeah, pan. I mean, the pan sequence. Originally, we heat pan to detect it with iodide SIMS. So with iodide SIMS, pan directly as a cluster. So if we took this pan with this iodide water and got an iodide pan cluster, it's very, very weak sensitivity. You almost can't see it. Turns out if you do this, you heat pan up and you decompose the NO2 off, and you let it go this chemistry, you can detect it on acetate, but we also find that you can detect this proxy radical, which is an interesting thing because now we're talking about detecting proxy radicals in the atmosphere also. But we can actually detect pan on 2 different masses now, and it's a nice safeguard because historically there have been talk about interferences on this mass. And so the TOF is an advantage over the old quad instruments when this was run. It used to be quad instruments. The only person that really has done this chemistry, as you see it here, is Greg Huey for a number of years. He's always on the DC-8, NASA DC-8 measuring pan with this method. So.
Just one other question. Did you say that with your Strat Sim system that you played around with pressurizing it and stuff?
No, that was the recommendation from the company.
Okay.
So the only iterations of this instrument that have flown in stratosphere were basically put in a big pressure can. So it's we looked at a radar today, and it was a pressure can in a pod. And so that's how they said we should fly it, is basically build a scuba tank around it and have your inlet coming out of that that's sealed. You know, this pallet bay isn't really built for configuration like that, the way the instrument came. So we could have either worked with a company and had them build a custom TOF for us, or we could understand the engineering challenges. And there's no other place I would have probably endeavored to do that, but knowing that NOAA had a lot of expertise in sending instruments into the stratosphere on the Global Hawk and the WB-57, this is why Drew Rollins is the co-PI, is that I don't have any experience with that. I'm a very good SIMS operator and developer, but I had no experience engineering things for the stratosphere, and Drew Rollins is in a group that has a lot of experience doing that. And so we teamed up to both develop the SIMS methodology, but also the ability to fly this thing in a more sort of elegant package that's flexible. So you could take this out of this pallet and you could rack it in a normal instrument rack and fly it that way. If we put it in a can, you can't necessarily do that. That's a whole different engineering challenge. But ultimately, this is just still a series of boxes and cables.
Great, thanks. That wraps up our hour, so let's thank Patrick for his interesting talk one more time.
Thank you, everybody.